All right, the next section we're going to cover is 2.4, measures of variation. So first thing, a couple of definitions. Says the range is the difference between the maximum and the minimum data entry in your set. So this is your range. Example, finding the range. 2 corporations have hired 10 graduates. The starting salaries are shown below. Find the range for the starting salaries for corporate A. So the range says take the largest, the maximum. So in this case, my maximum value was 47. And I'm going to subtract the minimum. In this case, my minimum is 37. So if I subtract 47 minus 37, my range is equal to 10. If I do the same thing for Corporation B, the largest number is 58. Smallest number is 23. So 58 minus 23 is equal to 35. And so my range is equal to 35. Conclusion? Well, if I look at the 2, it says that Corporation A has starting salaries closer together. There's less variation in the starting salaries. So there is more variation in Corporation B salaries, starting salaries. So here it talks again about variation. So both data sets in the last example, so both of these data sets have a mean of 41, a median of 41.5, a median of 41, and a mode of 41. So all 3 numbers, mean, median, mode, are practically the same thing. But both of them do vary greatly. And the reason they vary greatly is because, again, Corporation A have closer salaries, where Corporation B is much more spread out. So there's more variation in there. Right. So the variance then is the difference between the data entry X and the mean of the data set. So population variance says take each data set point and subtract the mean. So X minus mu, this is the data point minus the mean. For sample, it's the same thing, but again, we're using mu for the mean versus X bar if it's a sample population. The population variance then, the variance is actually, let me go back, sorry. This is not variance, this is deviation. The deviation, sorry, that's the deviation. The difference between the data sets. Right? So the population variance then says that we have, again, this Greek letter, which is sigma, only this is lowercase sigma. Remember that this was uppercase sigma, this is lowercase sigma. And the variance is sigma squared. So it tells us again to take the deviation. So we're going to take each data point, we're going to subtract the mean, we're going to square them, then we're going to add them all up, then we're going to divide by the number in the population. So again, this is order of operations that dictates how we do this. We take each data point and subtract the mean, then we square it, then we add each one of these things and divide by n. So this process is quite, there's a lot to the process because you have to do this for every single data point. So for every x, you have to do x minus mu. Then we're going to get the population standard deviation, which says take the square root of this thing that you've just done. So when it asks you to find this population variance or population standard deviation, it's going to get quite complicated. If you're doing sample variance and the sample population, or sample variance or sample standard deviation, they use s squared here and just s for the deviation. So sample is going to use the s, the population is going to use the Greek letters. All right, so example 2, find the population variance and standard deviation of the starting salaries for corporate A listed on the first example. All right. So we had 41, 38. So here's my data set, 41, 38, 39, 45, 47, 41, 41, 44, 41, 37, and 42. That's 10 data points. It tells me that my mean, my x bar, was equal to 41.5. So to do the variance, then I'm going to take 41 minus 41.5 and square it. I'm going to take 38 minus 41.5 and square that. I'm going to take 39 minus 41.5 and square that. 45 minus 41.5 squared. 47 minus 41.5 squared. 41 minus 41.5 squared. 44 minus 41.5 squared. 41 minus 41.5 squared. 37 minus 41.5 squared. And 42 minus 41.5 squared. After I do this, I have to sum all of these up. So I'm going to add all of those. So on my calculator, I'll do 41 minus, I do have to have parentheses, 41 minus 41.5 squared plus, because I can't add these up, parentheses 38 minus 41.5 squared plus 39 minus 41.5 squared plus 45 minus 41.5. Oops. Now see, I forgot a parenthesis. So if you forget a parenthesis, we're going to go back. If I go right here and I hit second insert or second delete, it'll insert a parenthesis when you miss it. And you will miss it, so keep an eye on what you're doing. 41.5. Select this a little bit. $41.5 squared plus parentheses 47 minus 41.5 squared plus 41 minus 41.5 squared plus, oh goodness, it's a square, plus, my fingers are getting a little fat, plus, let's see if I can use the pen, 44 minus 41.5 squared plus 41 minus 41.5 squared plus 37 minus 41.5 squared oh goodness. Delete that. Now square it plus, almost done, 42 minus 41.5 squared equals, uh-oh, now I have an error. Go to my error. Oh, I just want to delete that. Okay. Hit enter, and I end up with 88.5. All right. All right, so we said we added those up and we got 88.5. So you can see how tedious this can be. In just a few minutes, I am going to show you how to do this on your calculator, so it'll be a whole lot easier than trying to do this by hand. But in any case, we end up, because we know this is a population, we end up with sigma squared equaling 88.5. If I take the square root of both sides, I get sigma by itself instead of sigma squared, and that is approximately equal to 8.85. On your calculator, your square root button is above your squared, so second square root of 88.5, and that gives me, well, I was looking at the wrong number, sorry, 9.4. Sorry, 9.4. Oh, that's why it didn't work out. I'm so sorry. All right, let me undo this. I forgot the other part of the formula. It's 88.5. That was this top piece, but now I have to divide that by n. And in this case, there are 1, 2, 3, oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. So I'm going to divide this by 10. Divided by 10. And now this is 8.85. So now when I take the square root of 8.85, I can either write it this way or I can go ahead and simplify it. Then that's approximately, let me double check, square root of 8.85 equals 2.97. So it's approximately 2.97. That makes me happier. Definitely now matches what I had. So again, This is tedious. It's long. Imagine if you had 50 data points instead of just 10. Imagine if you had 300 data points instead of just 10. You can see how tedious this can become, which of course is why we want to rely on the calculator to help us find the answers. All right. We already mentioned that the only difference is instead of using sigma squared and sigma, we use S's when it's the sample. So the S is the sample, the sigmas represent population. And you're going to see really quickly that there's not a whole lot of difference depending on the number of pieces of data. If you only have 10 pieces of data, then there could be a significance difference. If it is, for finding the variance, it could make a difference because you do subtract by 1 here. And so it could make a difference. So if you have 10 pieces of data, then dividing by 9 is way different than if you have 2,000 pieces of data and dividing by 1,999. So oftentimes the population variance and the sample variance is very close to the same thing. All right. So this one says, in a study of high school football players that suffered concussions, researchers placed the players into 2 groups. Players that recovered from their concussions in 14 days or less were placed in group 1. The ones that took more than 14 days were in group 2. The recovery time in days for group 1 is listed below. Find the sample variance, this is sample, and standard deviation of the population, of the recovery times. So let's use our calculator this time and make this happen. All right. So remember from the last time, you're going to hit stat, and then you're going to go to number 1, which is edit, to enter the data. Then you're going to go back and we're going to hit stat. We're going to tab over to calculate, and then we're going to hit number 1, which is 1 variable stats. So I'm going to go to my calculator, go stat, I'm going to hit number 1, and I'm going to enter the data. Now remember, we had data in here from previous example, so it's still there. It's not going to go away. If I tab up to where my cursor is now on the actual L1 versus on a data point, you can see the data point is 223 here, but when I go up, now it tells me my list and what's in my list. So if I hit clear and then enter, it says we're going to clear list 1. Do not delete your data, you always clear it, because if you delete list data, you actually are deleting the list, not the data. So we clear the data. Be sure that you're always clearing out data. You can also just type over it, and it gets rid of it as well. Problem is with doing that is if you have less data pieces, you're going to have to do a lot of deleting of data. All right? But we have 4, enter, 7, enter, 6, 7, 9, 5, 8, 10, 9, 8, 7, 10. And we should have 12 pieces of data. So let's make sure that's what we have. Remember, this tells me I'm sitting in the 13th spot, but there's nothing in it, so I have 12 pieces of data. And let's double check and make sure that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that should be correct. So I'll go back to stat. This time I'm tabbing over to calculate. Number 1 for 1 variable statistics. Again, as long as your information is in list 1, you don't have to do anything here. You don't have to do anything to the frequency. So I just tab down to where it says calculate. hit enter, and again, this gives me a whole lot of information now. All right. So, oops, a bit. Right. So now I have my x bar, which remember is the average. Sum of all the x's. So if I were to add these data points up together, I would get 90. Doesn't ask me to do that. If I want to just sum them and square them, I would get 714. Again, that's not really asking me what to do, because remember in my formula, I have to subtract the mean in between. So whenever I look at the answers the calculator gives me, it's not subtracting the mean. It's just the sigma of all x's. This says square the x's and then add them up, but it is not subtracting the mean. So these two values really don't tell me a whole lot of information that I need. But the next two do. So I have x of x, s of x, and sigma of x. So s is the sample. The population is the sigma, and you can see that these both represent the standard deviation because it's not squared. That's what I want. It's the standard deviation. It's not squared, but it does give me both. It gives me the sample and the population. And if you look at them, there's not that much difference in them. And this was only 10 pieces of data. So again, the more data you have, the less difference there is between the sample and the population. It tells me I have 12 pieces of data. Again, it tells me what the minimum value was, which was 4. It gives me what we call Q1, and we'll talk more about what those values mean later. The median, Q3, and the max. So my example here asks me to find the sample variance and the sample deviation. Well, we said x bar is equal to 7.5, so that was the average. Then we had a couple of numbers that didn't mean anything, but then we had s of x and population of x, sigma x. One was 1.88, the other one was 1.80. Because this is a sample, I want to look at the 1.88. And S of x is the standard deviation. So that's the second part that it's asking me for. It's also asking me for the sample variance. And the sample variance says, take that number and square it. So in this case, 1.88 is my standard deviation. 1.88 squared would be the sample variance. And the calculator, when we do the one variable statistics, does not give us that. So the only way I can find that is actually, again, to go back to the calculator. Remember to go to the home menu. I have to hit second, quit, and I'm going to take the 1.88 and I'm going to square it. And I end up with about 3.5344. So this is an approximate value. Truthfully, this is also an approximate value. And that was, we said, about 3.53. And usually 2 or 3 decimal points is enough to go out. All right. So next one says using technology. So again, this is one for you to try. So spend a few minutes trying to see if you can get your calculator to do what you want it to do. It's got a lot more data pieces this time, so it's going to take you a little more time to enter them. So just be very careful. And again, we have 1, 2, 3, 4, 5, 6, 7, 8 times 3. We have 24 pieces of data. Make sure you get 24 pieces of data in there. Entering it is always most important. All right. So next, interpreting the standard deviation. Standard deviation is the measure of the typical amount an entry deviates from the mean. So how much does it actually move away from the mean? So if we look at this first one, these all have the same frequency. So they all have that same frequency. So that's like a uniform distribution. So it's very uniform. This one has the data is tight, is centered or tight around the mean. So again, here would your mean be, and the data is centered around the mean. This has my data more spread out. So if you look at the data, there's nothing here in the center, so this data is more spread out. And it's spread out because we have a larger standard deviation. I'm going to put SD for standard deviation. And if you look at it, standard deviation was 1.2, or standard deviation is 3. Here the standard deviation is 0, which is why there's nothing. Nothing moves away from the mean. Everything is centered right there at the mean. So everything has the same frequency. It's all the same. This one is centered more around the mean. This one is more spread out because of a larger standard deviation. All right? So what does this all tell us, and why is this important? Well, because standard deviation, we talked last time just briefly about looking like a bell curve. This is your standard bell curve. And your standard bell curve gives us a lot of information about how to interpret standard deviation. So standard deviation, a lot of the data sets that we're going to look at, a lot of data sets in real life fall into a bell curve. They look bell curved when you put them together with their mean, with their standard deviation. And so things like IQ scores, and that's why people will tell you whether you are above average IQ or below average IQ. It's all based on this standard deviation and the data that fits in there. Same thing with heights. You know, how do we know what the average height is of men versus women? And how do we know if you're super tall? Well, if the average height is only 5'8" and you are 7 foot, then you're going to be way out here. You're going to be so far away from the mean, you're going to be like an outlier. Medical standards, things like your cholesterol level. That's why they know when you need cholesterol medicine. All of them fall and take the same shape of a bell curve. So what this tells us is, here's your mean, and it says 68% of the data is going to fall within one standard deviation. So if your average height is 5'8", most people are going, 68% of the people are going to fall within one standard deviation of the mean. More importantly, or even better, 99% of the data, or 95% of the data falls within 2 standard deviations of the mean. And then by the time you get 3 standard deviations away from the mean, you have covered 99.7% of the population, or percent of the grouping. So again, if you're 7 foot, then you're going to be way out here, way away from the mean, because how many people do you know that are 7 feet tall? Not very many. So they're way to the side of the mean. Where if you're a Danny DeVito, you're going to be way out here on this side of the mean. So you're very far from the mean average. And this is called the empirical rule. The empirical rule is 68, 95, 99.7, and those represent the percents. 68 within 1 standard deviation, 95 within 2 standard deviations, and 99.7 within 3 standard deviations. So, how do we use this standard deviation? What does this mean to us? And how do we make that happen? In a survey conducted in the National Center for Health Statistics, the sample mean height of women is 64.2 inches and the standard deviation of 2.9 inches. Estimate the percent of women whose height are between 58.4 and 64.2 inches. All right. So, in order to do that, we're going to, all right, so in order to find out the percent of women whose height are between these two, well, if you look at your height, here's your mean. The mean is 64.2. We want to know this blue area. Well, if I just look at the chart, because this is so well defined at 58.4 and 64.2, since it's so well defined, I can say this blue area right here, I better change color pens. So this blue area right here, well, this total would be 68%. So this would be 34.13. And this blue area, according to the table, is 13.59. So if I add those together, 34.13 and 13.59, if I add them together, I have 49.72% of the population would be that height. And that should make sense based on this chart. Because again, this piece would be 34, this piece would be 13, add them together, and you're looking at roughly 49% of the population. This works out well because these numbers that they give us are the exact standard deviations from the mean. You're going to see some in just a little bit where those standard deviations don't match up on nice, pretty little endpoints like these do. And we can still get the answer. All right, so what happens then whenever data is not bell-shaped? Well, if it's not bell-shaped, we use what's called Chevyshev's theorem, and that helps us apply to all shapes of data. However, we're not quite as accurate. So it says the portion of data set lying within k standard deviations where k is greater than 1 of the mean is at least this formula. Now, what does that mean? In practical sense, it says for k equal to 2, that would be 2 standard deviations from the mean. Then we would have 1 minus 1 over 2 squared, or 1 over 3/4, 3/4, 1 over 4, or 75% of the data. For k equals 3, it would be 1 over 3 squared, or 1 over 9. 1 minus 1/9 is 8/9, or about 88% fall within 3 standard deviations of the mean. So Chevyshev's is good because it helps when things are not pretty and bell-shaped. The difference is the percentages. So with Chevyshev's theorem, we have 2 standard deviations are about 75% of the data. In the empirical rule, with the empirical rule, 2 standard deviations represents about, going back up to my chart, 2 standard deviations represents about 95% of the data. So that's the big difference. Using Chevyshev's theorem, you only hit about 75%, versus using the empirical rule, you hit 95%. Same thing with 3 standard deviation. Using Chevyshev's, you only hit about 88.9% of the data, versus the empirical rule, 3 standard deviations, hits about 99.6% of the data, 7. So the empirical rule is definitely going to give you nice, better, closer, accurate data within 3 standard deviations. But Chevyshev's isn't bad. I mean, 99, almost 90%, that's not bad for 3 standard deviations. And remember that this applies to any shape, so not just to the bell shape. So anything that doesn't look quite bell-shaped you can still make determinations and still find statistics based on those determinations. All right, so the example for Chebyshev says the age distributions for Georgia and Iowa are shown in the histograms. Apply the theorem to the data for Georgia using k equals 2. What can you conclude? So again, if you look at this thing, it's obviously not bell-shaped. Obviously not bell-shaped. You have a lot of people, we're looking at Georgia, you have a lot of people that are younger and very, very few people that are older in the state of Georgia. That's going to be common in almost every state. Again, look at Iowa. It sort of has the same, a lot of people all within the, till you get to about 60. And once you get to 60, it starts dropping. All right. So this says we want to know what happens when k is equal to 2. So if k is equal to 2, what that's going to tell me is, using Chevyshev's theorem, I'm going to take the mean, I'm going to subtract 2 standard deviation, and when I get that, I end up with 37.3, that's the mean age, and we're in Georgia, minus 2 times 22.3, the 2 standard deviations, and this is going to give me negative 7.3. And this is an age, remember, so we'll talk about that in just a minute. Then, if I take the mean plus 2 standard deviations, I'd have 37.3 plus 2 times 22.3, and that's 81.9, and that's the age. So if the mean is 37, which is right in here, we want to know within 2 standard deviations what percent of the population falls within 2 standard deviations. So we have to do the mean, and this would be a minus 2 standard deviations, to here, which would be plus 2 standard deviations. So we have to start with the mean and go on either side of the mean. This tells me my answer would hit negative. Well, of course, we know we can't have negative, so 0. And so the conclusion here then says that 75% of Georgia residents are between 0 and 81.9 years old. So anybody in this group, would be outside the 75%. And it's 75% because at k equals 2, we do have 75%. And that's based on this theorem right here. 2 standard deviations for Chevyshev's theorem is 75%. The next question it asks you says, is the age 100 unusual for a Georgia resident? And explain your answer. Well, 100, the age 100 is well above 2 standard deviations. And since it's well above in this direction, then to reach 100 in Georgia is very uncommon. So uncommon. Which, again, shouldn't surprise anybody, because how many 100-year-old people do you know? So 89, yeah, and that would hit 75%. But once you start getting much more than that, they're going to be more and more uncommon. And that's exactly what this chart shows. Again, most of the people are within this age group, but by the time you hit 85, then you really start dropping. All right, and that will wrap up section 2.4.